So this is the subdifferential of pointwise maximum functions. Okay, so it depends on the subdifferential of all the activated functions at this point. Okay, take the activated functions, consider their subdifferential. Then we take a union of these sets and then consider the convex whole. And last time we see that many examples can be forced into this case. Like L infinity norm is a pointwise maximum over all the coordinates. Eigenvalue is a supremum, can be written in a supremum form. And moreover, for this nuclear norm, it can be also written in a supremum form. So let X be any matrix, any arbitrary real valued matrix, not necessarily symmetric. X is an arbitrary matrix, and every matrix have a unique singular value decomposition we call SVD. The X can be decomposed as U sigma times V transpose. Well, U and V are also orthonormal matrices, and the sigma is a diagonal matrix. So, for example, if X is a tall matrix, then this can be decomposed as U. This is sigma. And this is V transpose. So this is M by N. Then this is M by N. This is M by N. And this is M by N. And sigma is a diagonal matrix with and the diagonal elements are the singular values of this matrix. If this matrix has rank R, then there are R singular values. The rest are 0. This decomposition applies to any arbitrary matrix. So this is the decomposition that we usually use for a matrix, singular value decomposition. Okay, so X can be written in this way. Basically, you can view this as this sigma is the spectrum of this matrix. And so every matrix is associated with a diagonal matrix up to some linear transformations. U and V, these two are orthonormal transformations. So it's just a sigma, a diagonal matrix, apply some orthonormal transformations, we can get to this matrix X. And then we define fx to be the sum of all the singular values. Sum of all singular values. Sigma I is the ith singular value. This is a function, takes a matrix and sums over all the singular values of this matrix. And we can characterize this subdifferential. So this is called the nuclear norm, sum of all the singular values of a matrix. Okay. If we consider the maximum singular value, then that is called the operator norm or spectral norm. But here is the sum of all the singular values. We call it nuclear norm. and it is a norm. Now, this nuclear norm can be rewritten in a variational form. Can be written in this way: is take the trace product between A, B transpose and X, while A and B are orthonormal, and then we take the supremum over all orthonormal A and B's. Okay. So basically, you look at all possible orthonormal matrices A and B, so that this matrix inner product achieves the supremum value. Okay. And orthonormal matrix, you can check the definition. They are like the rows, columns. They are orthogonal and have unit lengths, unit norm. Okay. So this nuclear norm can be characterized in this way. And we can check that this function, this definition, the supremum is achieved by choosing A equals to U and B equals to V in the SVD form of X. If X has that SVD, then this supremum is achieved by these two choices. Okay, and also the gradient of this dot product, the gradient of this linear function with regard to X is basically this coefficient A B transpose. Okay. So by the pointwise supremum subdifferential rule, the subdifferential of this function can be characterized by the activated function. So this inner product is the supremum value is achieved at this point. So it's basically, and the gradient at every point is given by A B transpose. So the subdifferential is basically U times V transpose, okay, by the pointwise supremum subdifferential rule. So this belongs to the subdifferential of F. In fact, the subdifferential of this function is more general, and this is just one special element in the subdifferential set. And actually, this is a convex function. This is a norm. It's a convex function. And a matrix. This function takes matrix as inputs. Okay, so these are the examples of pointwise maximum or supremum functions that we see in practice. So you can see for many norms, vector norm, matrix norm, or singular value eigenvalues, they are naturally related to this these two forms, pointwise maximum and pointwise supremum. And then we can talk about their subdifferential. Okay. And then we need to pay attention to the direction of the subgradients. It is possible that the subgradient may point toward and not necessarily the descent direction. For example, for this two-dimensional function, at this point, at this 1, 0 point, these two are two proper sub gradients. You can check, just check that inequality, that definition of subgradient. These two are subgradients, but one of them is pointing toward this direction, the other is pointing toward this direction. And we can see clearly following this direction. So this is the negative of G1, okay? And this is negative of G2, right? So imagine if we do gradient descent following these two subgradients. Okay. Then you can see that if we follow the first choice, then we are good. We are going towards the minimum point, right? So the value is decreasing. So this is a good direction. But if we follow this subgradient direction, then we are going outside. So the function value will actually increase. So this shows that the sum of the subgradients may corresponds to a increasing or ascent direction. This is because subgradients basically it is a set. It may contain so many different directions. And when the function is not continuous, not differentiable, one can change directions significantly without violating the definition of subgradient. So basically, at those non-differentiable, like this is a non-differentiable point. At those points, the function may have lots of subgradients, and so some of them may be pointing toward the wrong directions. Okay. Therefore, if we do subgradient descent, if we do projected subgradient descent, right? So here, instead of using gradient, we use subgradient because the function may not be differentiable. If we do that, this may not guarantee the function value will decrease every time. We don't have that guarantee. Okay, as we also see this in this example, right? So therefore, in the analysis, we will look at the best function value that we achieved up to now. Okay. So we denote this f best t is the minimum function value we achieved in the first t iterations. Okay. Because the algorithm may fluctuate in, sometimes the function value is going up, sometimes going down. So we take the minimum, we look at the minimum because we are doing minimization. Okay, so this is the convergence criterion. So we will keep tracking this value, the best value among the first t iterations, and then analyze the gap between this value and the optimal value. Right? The optimal value is the minimum value of a function. Okay. And then before we start analyzing this algorithm, we need to specify our function class. Right? So because now the function is not differentiable anymore, so we no longer talk about gradients, and we will not have those smoothness conditions that we introduced for gradient methods. Okay. So therefore, here we consider the class of Lipschitz continuous functions. And this is basic to say that the function changes slowly following by a certain governed by a certain constant, Lipschitz constant. Okay. So for any x and z, the function value can be bounded, difference can be bounded by the distance between the variables up to a constant, and Lipschitz continuous functions. Remember in the previous lectures when we defined the smooth functions, one of the definitions is to say that the gradients are Lipschitz continuous, right? So the smooth L smooth means that the gradient, the function is differentiable and the gradient is Lipschitz continuous. Right. But here we are talking about possibly non-differentiable functions. So there's no gradient anymore. So instead, we talk about the function, the change in the function value. So we consider this class, Lipschitz continuous class functions. And many functions falls into this class, L1 norm and many other norms. Yeah. And the key technical tool to the analysis is this lemma, which characterizes the distance of your current variable to the optimizer. Right. So here we keep tracking this distance metric, and this is the distance in the t+1 iteration. So we will show that this result shows that this distance can be bounded by your previous distance. This is a previous distance in the previous iteration. Can be upper bounded by the previous distance and with some additional terms. But it is not clear about the sign of these terms. The last term is definitely positive. Now the second term is this difference is definitely positive because this is the optimal function value, the minimum value. So this is a positive term, and we are subtracting a positive term and adding another positive term. So it is not that clear what is the final sign of these two terms. Therefore, you can see this distance may not necessarily be monotonically decreasing because these two terms, we are subtracting a positive term and add another positive term. However, we can see that these two terms, for the first term, it has coefficient eta t, which is the step size, right? For the second term, we have eta t squared. So the second term is quadratic in the step size. So intuitively, if I choose a relatively small step size, then the second term can be order-wise smaller compared to the first term, right? So if I choose a very small eta t, this one will be much smaller than this one. And therefore, hopefully the second term dominates. If the second term dominates, then we are subtracting a big positive number. And then this distance may be monotonically diminishing, and we can hope for convergence. Okay. So you can tell from this key inequality that the step size should be carefully chosen so that we are making a proper or sufficient progress between the iterations.
Is that OPT the minimum value of f?
Yes, it is defined as the minimum value, the minimum of x.
G is the gradient.
G is the subgradient we use in the algorithm. Yeah.
All right.
Yeah. So this is 4.1. So we are looking at this projected subgradient descent. Okay, the proof is actually pretty simple. So we basically start from the t plus 1, okay? And notice that xt plus 1 equals to this one by the update rule of the projected subgradient descent. Okay, so this is plug in the definition of xt plus 1. This is algorithm update. Now x star is your minimizer. So it must be in C because x star is the minimizer of this constraint problem. Okay. So we are looking at this problem. Right, we're looking at this constraint problem. So the minimizer must satisfy this constraint, right? So x star must be in the set C. Therefore, x star, I can claim it must be equal to the projection of itself because it is in the set C. It is within the set. And then we have shown that this projection is a non-expansive operator. So the difference between projection is less than equal to the difference between these variables, these 2 points. Okay. We have this non-expansive property. So we can get rid of the projection. And then this is a quadratic term, so we can expand it. So this is equality, just expanding this quadratic term. And we will merge these 2 terms together so that we have this is the distance in your previous situation, the t situation. Okay, and the rest of the terms are this is a cross term and this is another quadratic term. Now, for this cross product term, we simply utilize this subgradient inequality. Why? Because in the algorithm, GT is a subgradient of at xt. Okay. GT is a subgradient at xt. Therefore, for any z, this inequality holds by the definition of subgradient. And here we specify z to be x star. We simply specify z to be x star. So we will have this inequality by subgradient. And this allows us to bound this inner product in terms of the function value gap. And this gives the desired result. Okay. Now, based on this result, we want to further derive some convergence rates or convergence results. And apparently here, as we discussed before, the choice of step size is critical. We need to choose a proper step size so that this term dominates. Right? We want to subtract a positive number. We want the last term to be suppressed as much as possible. So here we can first consider a very popular choice of step size, which is I set eta t to be fxt minus the minimum value divided by gt square, the L2 norm to the square. This is because in this this is basically to balance these 2 terms. Right? If you make these 2 terms equal, you can check. If you want to make them equal, then roughly eta t is this difference, function value difference divided by gt square. Okay, that's why we pick this choice here. Now, if you choose this step size, you plug it into that inequality, we will get this result. Okay, you can check, we will get this result. So this step size guarantee that those 2 terms will give us a negative term. So here we are subtracting a positive number. Okay. So this is a nice result because this shows that this distance is monotonically decreasing over the iterations. Monotonically decreasing. However, on the other hand, this step size requires the knowledge of the minimum value. Okay. We in the algorithm we will compute GT, so the denominator can be computed. The norm is not a big problem, and we need to evaluate the function value at each iteration. Also, we need to know the optimal function value beforehand. So if you don't have that information, well, then you cannot use this step size. This is the limitation. But the nice thing is that it guarantees a monotonically decreasing distance. Let's go back to this example later. And the first, let's go to this main convergence result. Okay. The main convergence result says that suppose f is convex and the Lipschitz is continuous. Now we apply the projective subgradient method. Okay, with the Poyax step size. This is the step size that we just described. Okay. No. With this step size, okay. We can prove a sublinear convergence rate, like the best function value for the first t iterations minus the minimum value is roughly is a constant 1 over square root of t. It's roughly 1 over square root of t. So let's first look at the proof, which is also very simple. So we start from 4.5. Right? 4.5, we plug in this Poyax step size rule into that in P-lemma. So we have this 4.5. Okay. Now, based on this one, rearrange this inequality. Okay. Rearrange this inequality, you will get this one. Okay. It's nothing but a rearrangement. Rearranging this inequality. Okay. And then you see on left hand side you have function value gap. Right hand side you have the difference between two distances. Now GT I can bound it by GT L2 norm. I can bound it by LF because for convex Lipschitz continuous functions we can show. Now this is a separate result for convex and Lipschitz continuous functions. We can show that the subgradient, the norm of the subgradient, is bounded by LF. It's bounded by the Lipschitz continuous parameter LF. So those GT norms can be bounded by LF to the power of 2. Okay. So we bound them by the constant. And now this can be since this is this can be upper bounded by a constant, then we can just sum over this inequality over the iteration t, and these terms is a difference between consecutive iterations. So when we sum them up, the intermediate terms will cancel with each other. So we sum them up. The left hand side is basically this term summing from k from 0 to t. Okay. And these terms cancel out. We only have the starting term and the ending term. This is a constant, right? Now we can further drop this term because it's we are minus a positive number. So we drop this term. We have initial distance times LF squared. on the left-hand side, these two, I can relax fxk by the best function value, by the minimum function value I achieved in the first t iterations. Okay, and there's a t+1 because the summation has t+1 terms. Okay. Each of these terms will be lower bounded by this guy, right? And then we have t+1 of this term, so it's t+1 times this. And this already gives the convergence rate. You just move t+1 to the right-hand side, take the square root, and we have that result. Right. So this proves the convergence rate of projected subgradient descent for convex and Lipschitz continuous functions under the Poyak's step size, under this specific step size. Yeah. And now let's look at a very classic optimization problem, which turns out to be a special case of this projected subgradient descent method. The question here, the problem here is like we have two convex sets, C1 and C2, and suppose they have non-empty intersection. Now we simply want to find a point in the intersection. We simply want to find a point in the intersection. Now this problem can be reformulated as the following problem. Well, we want to minimize the distance, the maximum distance between x to set C1 and x to set C2. The intuition is that if x is in the intersection area, then the distance to C1 should be 0, and also the distance to C2 should also be 0, right? So we kind of characterize this inclusion equation using the distance, right? If x is in the intersection, then both distance would be 0. Therefore, here we simply consider the maximum of these two, and we minimize this maximum distance. So ideally, if you can find an x that makes, this term 0, then both of them will be 0. And both of these distance will be 0. And that implies that x must be in C1 and x must also be in C2. So x is in the intersection. Well, the distance is simply defined in this natural way. Okay, distance between a point and a set. So we fix this x and we look for all the points in Z in the set, and that has the minimum distance to that point. And for this problem, we have a classic algorithm. This is a very simple and classic intuitive algorithm. This is called alternating projection algorithm. Well, you start from any initial point. Say you start from a point in C2. What you do is that project this point onto C1, and then you get a new point. And then you start from this point, you project it back onto C2. You do this alternatively. And eventually it will converge to a point in the intersection part. Okay. So this is a classic alternating projection algorithm, but it turns out that this algorithm can be understood as subgradient method with Poyak's step size rule. So we will show how we can get to this algorithm by starting from the subgradient method. So first of all, in the subgradient method, so the objective function is this one. This is our fx. Clearly, it is not differentiable because it is a maximum of two pointwise maximum of two functions. So there will be some non-differentiable points. And moreover, since it is in a pointwise maximum form, so we can apply the subdifferential rule to calculate the subdifferential of this function. And that rule simply says the subdifferential is basically the subdifferential of the activated function. Well, this I is the distance that achieves the maximum among the two. Okay, so this I is the activated distance function. Okay. So take this activated function and consider its subdifferential. This would be a subdifferential of our fx of our pointwise maximum function. Okay. So therefore, in our algorithm update, our GT, our subgradient is simply picked from the subdifferential of the activated distance function.
We dive into this a little bit more. Like, what does it mean to be an activated distance function?
Yeah, it means that at this point xt, you compare these two distances, right? And the one that has the higher distance, the larger distance, is the activated one, because here this function is defined as the maximum between the two, right? So at one point xt, you compare these two distances. The one achieves the maximum distance of the two is called the activated one, right? So this is consistent of the with the pointwise maximum function that we defined. Consistent with what we defined here, like these. We are looking at those FIs that achieves the maximum. This is called activated.
Okay. Close that up.
Okay. And the question is, how do we suppose we have suppose CI is that distance CI is that active distance function. Now, how for that distance function, what is the subdifferential? What is the subdifferential? And the red part, the red equation shows that, and this is another classic result, but this subdifferential is actually differentiable. This distance function is actually differentiable. And so the subdifferential is essentially the gradient. And it can be shown that the gradient takes the following form. The gradient takes this form. It can be shown that. So GT, which is the subgradient, actually in this case corresponds to this gradient of the activated distance function. And the last comment is a short comment on how to prove this. Basically, you have to show that the gradient of this quadratic distance function can be written in two different ways. And then from there, you can solve for the gradient of the distance function. But I think we will see something similar, more general in the later lectures. But here, I will not dive into the details. Okay, so given this formula, so we have this subgradient, we plug it back to the subgradient method, and that is our result. Okay. Now, yeah, and you realize that this GT has a unit norm. Why? Because if you take norm of GT, the denominator is the distance between xt to ci, but the numerator is the distance between xt and its projection point on ci, which is exactly the distance, right? So the GT has a norm 1 as unit norm.
So it's just a direction.
I mean, so GT, if you take the norm of GT, then it's just the norm between xt minus pc xt divided by the distance. Right? And the numerator is exactly the distance. This is exactly this one, by definition. So it is just 1. So GT has unit norm. And this helps simplifies the calculation. But okay, so write down the update rule of subgradient descent. This is the update rule of subgradient descent. And the GT we have shown in the previous slide. This is GT, plug it in. This is GT. And eta t, we use the Poyak's step size. So this is eta t. This is eta t, this is GT. I simply plug them in to this update rule. And then simplify them. Look, these two distance cancels out. GT has unit norm, so this is 1. So we only have this term left. And then x cancels with x. So what is left is simply the projection of xt onto ci, onto the, well, ci achieves that maximum distance among the two. So the algorithm is very simple. Use the following, you start from xt. The next iteration is basically projecting xt to the set. So there are two sets, right? You just project xt to the set that is farther away from it. Okay, and then you go back to this figure. Suppose you start from a point in C2. Then the algorithm says, okay, you project this point to the set that is farther away from this point. Apparently, C1 is far away from from this point than C2, right? Because distance between point and C2 is 0. So you simply project onto C1. Once you project onto C1, and then for this point, you project it onto the set that is farther away. And now, since it is on C1, so you have to project it on C2, right? So it is always alternating between these two sets, always alternating between this. So this exactly recovers this alternating projection algorithm. Right. So this algorithm is very intuitive, and you can imagine, right? If you keep projecting back and forth, alternating between two sets, maybe you will end up with something in the intersection. But there are something critical here, like here, these two sets must be convex. Otherwise, there's no guarantee you can always find a point in the intersection. And second of all, about convergence rate, it is not that clear how to analyze this algorithm from this alternating projection form. But if we consider it as minimizing such a pointwise maximum function, then this algorithm is essentially a subgradient method applied to this Lipschitz function. You can verify this is indeed a Lipschitz function, Lipschitz continuous function. So everything is perfectly falls into this subgradient descent theoretical framework. Right. And this convergence rate applies. This result applies to that problem. It is convex because those two are convex sets. So the distance to a convex set is a convex function. Lipschitz continuous, you can show that, and then this subgradient methods with Poyak's step size, we have just shown that is equivalent to the alternating projection algorithm. Okay. So for that algorithm, we have this 1 over square root of t convergence guarantee in terms of the function value gap. So this shows that if you do alternating projection, then the distance between the point to you can sort of say the distance between the point and the intersection area is gonna be diminishing at the rate 1 over square root of t. Okay. Because that distance is the function value of that problem. It's the objective function value of that problem. Okay, so this is a general result, but it covers this one as a special case. Okay, a very classic problem. And in fact, you can probably do intersection of multiple convex sets. Doesn't really change the problem. If you have three or four convex sets, you can add more distance terms to this maximum. So but it doesn't change the problem structure. You're still dealing with a piecewise linear, pointwise maximum function. Right? So everything would be the same, but the algorithm would be a bit different. This would be the algorithm. So say you have three sets. You start from a point in C1. Now you will project this point onto. Now you have C2 and C3. Which one will you project? You will project it onto the one that is farther away from your current point. Right? So no matter how many sets you have, you always pick the one that is far away from your current point. Project onto that one. Okay, so this is about what the convergence rate of this. So there are two things, right? When you read this kind of results, first of all, what is a function class? Right, the first sentence specifies the class of problems that we are dealing with. Convex if it's continuous function. Then, second of all, what is your algorithm? The second sentence specifies we are looking at projected subgradient method with a special step size, with this Poyak's step size. And we just mentioned that the Poyak step size has a limitation. We need to know the minimum function value. Right? But in practice, for a optimization problem, we don't know what is the minimum value unless it is a trivial problem. Right? So the question is, can we avoid? Are there any other step sizes that we can use in practice, and that also gives the similar convergence guarantee? Okay, and this is a more general result, more general convergence result. So the function class is the same, the algorithm is the same, but here we do not specify the step size rule. Okay? We do not specify this eta t. For a general eta t, this will be the convergence rate. Okay? And the derivation is exactly the same, but you just don't. You just follow the previous derivation, but you don't plug in the Poyak step size. Instead, you just keep it as general as eta t. And the question is, can we choose any practical eta t, and then the resulting, the right-hand side can still diminish at a certain rate? There are several choices. First of all, we can try a constant step size. If we set eta t to be a constant, then you can plug it into the right-hand side, and that simplifies to, you have t times eta t squared in the numerator and the t times eta t in the denominator. So that roughly gives you this number. Okay. And you see this, the right-hand side does not change with regard to t. So if you use a constant step size, it may not converge. There's always a gap. The right-hand side does not diminish. So we want to choose a step size so that this term is finite, but this term goes to infinity. Okay, because you see this term is in the numerator, and this sum is in the denominator. We want to make sure, ideally, we want to make sure this summation is finite. It's a sum over squares. Right? At the same time, this one is divergent to infinity. Then we can have, then the entire fraction number will goes to 0 in the end. So we want to choose a eta t that satisfies these two conditions. And the good choice is 1 over square root of t, because on one hand, if you set eta t to be 1 over square root of t, then this one is roughly sum over 1 over t. Summation over 1 over t is roughly log t if you approximate it using integration. Whereas sum over 1 over square root of t is roughly square root of t. Okay. So if you pick this one, then you have log t over square root of t for those two summations. And you can see that, well, both of them will diverge to infinity as t goes to infinity, but the denominator is much bigger than log t. Log t is a very small number if t is very big. So eventually, asymptotically, this term can be sort of ignored, and the entire term will be dominated by 1 over square root of t. Okay, so this rate is roughly log t over square root of t. Log t over square root of t. And we usually ignore the log factors because they are not dominating factors. Okay. Yeah, so this is a this is a more practical step size. Doesn't rely on any prior knowledge, right? It's a fixed diminishing step size group. Okay, so this is about subgradient methods for convex and the Lipschitz continuous functions. And it also has convergence guarantee for strongly convex and the Lipschitz continuous functions. Okay. So now here we consider a smaller class of problems. They are strongly convex, so they are more, the requirement is more stringent. So the class of problems will be smaller. Okay. Strongly convex and Lipschitz continuous functions. It can be shown that for these problems, if we choose this step size, roughly 1 over t, if we choose that step size, then the convergence rate is roughly 1 over t. Okay. So this is for strongly convex problems. If you compare this with the convex result, with this result, convergence is 1 over square root of t, but here is 1 over t. So clearly this one is much faster. 1 over t decays faster than 1 over square root of t. Okay, so this is the result for the class of strongly convex problems. And the proof is very simple, so I will only talk about the difference. Okay, the only difference is here. The only difference is this about this lemma. This is what we can do for convex problems. Okay. But for strongly convex problems, this term can be even smaller. Okay. You see here the coefficient of this term is 1. Okay, for convex problems. But for strongly convex problems, we can improve it with an even smaller coefficient. So this is something less than 1. And then you can imagine there will be an exponential decay on the first term if we unroll this inequality. Once we have that, the rest of the step is basically rearranging the terms and plug in the step size, and you get the result. So I will so really so I will not go into details, but they are easy to follow. And so here the main point is that this this term can be further improved. Why? Because when we prove this result for convex problem, then this is the proof. We use this inequality. And this inequality is essentially convexity between x star and xt. Is the definition of convexity. But for strongly convex problems, this inequality can be even stronger, right? There will be an additional quadratic term for strongly convex problems. If you add that to this one, then we will have an additional quadratic term, this one. And those two terms combined together will give us a diminishing coefficient. So that is the only difference. So here we will apply strong convexity instead of convexity. Okay, and then we can summarize this subgradient methods. For convex and Lipschitz problems, we pick this step size, and we will have this convergence rate, 1/square root of t. For strongly convex and Lipschitz problems, we pick a 1/t step size, and the convergence would be faster, 1/t. Right. And for the iteration complexity, it's basically we can solve from here. Set this one to be epsilon, so we require this many number of iterations to achieve an epsilon accuracy. 1/epsilon square for convex problems, while we only need 1/epsilon for strongly convex problems. Okay, so this is the subgradient methods for solving convex Lipschitz minimization problems. And there's another type of subgradient methods which are to solve convex concave saddle point problems. This is a very another important class of problems. Here I will just give a brief overview of this part. So instead of doing minimization, here we are looking at a function of two variables, f, x, y. And we want to minimize over x and maximize over y. So this is like a saddle point problem. You want to do minimization on one variable and the maximization on another variable. For example, many games, two-player games can be formulated into this problem. First player want to minimize the cost. Second player want to maximize its profit. Maybe they are competing with each other. That is exactly this minimax problem. And it has different formulations, but here we focus on one class of these problems. We assume this function is convex in x and concave in y. Meaning that if you, for every fixed y, fx y is a convex function in x. For every fixed x, it is a concave function in y. And you can sort of see the symmetry between these two, right? For every fixed y, fx is a convex function, and we are minimizing over x. So it is a convex problem. For every fixed x, y is a concave function, and we are maximizing over y. So it's also a convex optimization problem if you consider negative, if you just add a negative sign to the objective function. Maximizing concave is symmetric to minimizing convex functions. So they are exactly symmetric to each other. And we assume these variables are in a bounded enclosed convex set. So I mean, the optimization is over a bounded closed convex sets. Yeah. This form has many applications in game theory and robust optimization. And yeah, well, the robustness comes from this maximization, right? For example, you want to minimize usually the minimization part is about the cost. You want to minimize a certain cost. But the maximization part is about maybe the worst case scenario over all the possible y's. Maybe y is the environment. You are considering, in the inner part, you are considering the worst case environment that will give you the highest cost, right? And for that worst case scenario, you want to minimize this cost. So this is called robust optimization. You want to optimize on the worst case scenario. This is the worst case. The maximization is the worst case scenario. And under some mild conditions, these two can be max, min, and max can switch their order. So this is equal to its dual formulation, max, min, basically switch their order, but under some mild conditions. And this is an example of a saddle point problem. Well, this is basically the landscape of the two-dimensional function, x and y. And you can see that if you fix a y, then the function looks like a convex function, right? And you can do minimization. If you fix an x, function looks like a concave function, and you can do maximization. Now, you put these two together, you are looking for that saddle point. You are looking for the saddle point. And this saddle point, x star, y star, satisfies this saddle point inequality. This is the optimal point, the definition of optimal point for this problem. Basically, for this, at this point, yeah, okay, at this point, if you switch y star to any other y, that will only lower the function value. Okay. Think about that. We are maximizing over y, right? So at that point, if you only change y, you will only lower the function value. So that means y star is the kind of the optimal point. And at this point, if you fix y star and change x star to any other x, it will only increase the function value. Okay? But we are minimizing over x. So this also shows that x star is also the kind of the optimal solution. So this is like a sort of like a Nash equilibrium. At this equilibrium point, wherever you go, you always end up with a suboptimal solution. And we can just extend the subgradient method to such a saddle point problem. And the update rule is pretty simple if we write it in a vector form. So basically in the t's updates look like this. This is a current variable x t y t. I simply do a subgradient descent. Okay, see gxt is the subgradient. So gxt is the subgradient with regard to x. Okay. And gyt is the subgradient with regard to y. But here you see, because x and y, x is minimization, y is doing maximization. So you can see on x, I use a subtraction to do descent. And on y, there are two subtractions, but they cancel out. So actually, I'm doing subgradient ascent on y because I'm doing a min-max problem. Right? I want to maximize over y, so that's why I need to make this to be positive. Okay. But I still want to write into a standard form. So I just write it. I introduce a negative sign so that I can put a negative sign. So this is basically the projected. Now this is projection. Projected subgradient descent on x and subgradient ascent on y. Okay, a very simple algorithm. The straightforward extension of the subgradient descent. And we will use this metric to measure the optimization quality, because in this problem we are neither doing minimization nor maximization. It's kind of a combination. It's a mixture of two. We are minimizing over x, maximizing over y. So the right way to measure the optimality is to consider this one. So for a given point x and y, how do we measure its optimality from an equilibrium point? Well, we denote the function value at the equilibrium point as f optimum. Okay. And I'm looking at, for this given x, I'm looking at the maximum value over y and subtract this equilibrium point. This is to measure the optimality, one-side optimality of x. Right. Because for x star, so you can say this, f x star y star, because it's the equilibrium point, it equals to fx star y, the max over y. Right. It also equals to fx y right. This is an equilibrium point, meaning that it equals to, if you fix x star, then y star is the best response to x star, and by symmetrically, y star is also the best response to x star. Right. So we use this one to measure the optimality about x. So this part minus f x star y star. And we use this one to measure the optimality about y. That's why we have the second term, which involves minimization. And then we can just cancel out this optimal value. So the optimality metric for saddle point problems is defined in this way. Okay. The first maximization part is what is the best response to your x. You have fixed x, and you're looking at the best response to your x, right? So player one chooses x. What is the best response for player two? Second one is the best response for y. But player two chooses y. What is the best response of player one? Okay. And if this two has no difference, if this max minus min is zero, then meaning that means that x and y, they are best response to each other, which means they achieve an equilibrium point. Okay, so this part is a little bit, I think it still follows the intuition, but because it's a saddle point problem, so a little bit more complicated.
Yeah, makes sense.
Makes sense, right? So it's just like a two-player game.
Sigma is the error metric, right?
Yeah, this epsilon. Yes, epsilon xy. This is the metric for convex concave saddle point problems. We have 1 minute left. Maybe we can first overview the convergence rate. This convergence rate is about, for convex concave problems, and suppose they are Lipschitz continuous, and let dx dy be the diameter of these constraints, basically the diameter of the domains of x and y. Then the projected subgradient method satisfy this criteria. You see this convergence error, this convergence metric. So after running t iterations, the convergence error can be bounded by the right-hand side. But the right-hand side is basically some constants, but pay attention to these summations. It's sum over square of the step size divided by sum over the step size. Okay, we have seen a similar structure in the subgradient methods for minimization problems. Well, these x hat t and y t, okay, they are special. They are not the variable that you obtained at iteration t. They are a weighted combination of all the points that you obtained in the first t iterations. It's a weighted combination. And these weights are determined by step size. But this can be doable because once you run this algorithm for t iterations, given the step size, you can calculate this x hat and t hat. Right? Once you run this algorithm, you can always keep track of these two variables. Yeah, and since this part, the structure is similar, so we will choose this step size. Choose 1 over square root of t, and then this error will be decaying at roughly 1 over square root of t. So the convergence rate is very similar. Maybe next time we will briefly talk about this proof. Yeah, but you can look at this, review these saddle point problems, and see if you you can have a better understanding of this convergence metric. It's just like a two-player game. Okay. So we will continue next time.
Professor?
Oh, we have a comment. Okay, yeah, you can yeah, I think you should submit both of them. Since you have the code, why not just submit it? Okay. But for the report, I can accept any files, PDF or Word.
Okay. Professor, I have another question.
Uh-huh.
Say, for